Okay, so let's go ahead and talk about Unit 9. We're to the last unit of APES, except I messed up a little bit this year and taught 7 and 9 together, which I think is good. I like teaching 7 and 9 together, but I probably should have done 8 first. And then 9 is a nice wrap up of all of our concepts that we've gone over in APES this year. But I think it's okay because Unit 8 doesn't really have any content that falls into Unit 9. So I think it'll be all right this year if I just go ahead and do 8 after I teach Units 7 and 9, but I think in the future I'll do 8 first. Okay, so I'm going to do the first 2 sets of notes here, which is 9.1 and 9.2. 9.1 is stratospheric ozone depletion, and 9.2 is reducing ozone depletion. So let's talk about stratospheric ozone and where we find it and what it does for life on the planet. Okay, so stratospheric ozone is found in the stratosphere, which is a couple of miles above where airplanes fly. And the ozone that's up there actually absorbs UVC and all of the UVC radiation actually that comes from the sun, and most of the UVB radiation that comes from the sun. You can see that over here in this visual image. And then you can also see that the UVA radiation is actually, a lot of it is able to move or actually hit the surface of the planet, so where we live. And we just get a little portion of, or a small portion of the UVB radiation that's coming from the sun. So this is actually really important because if we did not have the ozone layer absorbing this radiation, we wouldn't have life on our planet. And the reason being is that UVB and UVC radiation cause significant tissue damage and it mutates DNA. UVC is actually the most dangerous UV radiation that comes from the sun, and UVB is next dangerous, and then UVA is still harmful, but it's not as dangerous as the others. So what are some of the human health benefits? Well, the ozone layer helps us to prevent skin cancer, and it also reduces our incidences of cataracts. However, some of we need to be protecting ourselves as well. So we should be wearing sunscreen and we should be wearing sunglasses when we go out in the sun so that we can protect and preserve both our skin and the lenses in our eyes. UVB and UVC actually mutate the DNA, and so that's what causes that skin cancer, and it's what causes the deterioration of the lens in the eye, and the lens of the eye starts to get cloudy, and it impairs the vision of the person that is actually, experiencing that cataract. So another thing to remember is from Unit 7 that tropospheric ozone is actually a respiratory irritant. We know that. We also know that it damages plant tissue. We saw that in our seedling lab. And it can be a precursor to photochemical smog. Okay, so those are all things that you need to know about the tropospheric ozone. All right. So how does ozone actually absorb this UVB and the UVC radiation? Well, what it does is the UVC radiation will hit the O3 molecule that's in the atmosphere. Oh, I guess this is an O2 molecule. Okay, so it'll hit an O2 molecule, and it will split the O2 molecule into 2 oxygen atoms, as we can see here. When these free oxygen atoms for this reaction combines with an O2 molecule that's just free floating as well in the atmosphere, that's the atmospheric oxygen that we breathe in, then it'll form O3. Those two join together and it forms O3, which is the ozone. Okay, that's how we get the buildup. We already know that from doing our drawings on our chalk drawings that we did in Unit 7, so you guys should be very familiar with that reaction. UVC, what it does is it causes this reaction to reverse, and it actually, when the UVC hits this molecule, it gets absorbed, the energy gets absorbed, and it causes the reaction to just go in reverse. And instead of O3, now it breaks off because of the energy burst. It breaks off one of the oxygens, and then that oxygen's now free floating and it can combine and form, another O3 molecule, or it can join with another oxygen and form an O2 or whatever. Okay, so this continued formation and breakdown of O3 in the stratosphere absorbs basically all of the UVC that's hitting the planet. So that's incredible that that happens, and it helps preserve life on the planet. It also absorbs most of the UVB, like we saw in the previous picture on the previous slide, and so that just protects our planet, which is fantastic. Now, of course, there's man-made ways that we break down the ozone layer, and so the number one thing that you need to know for apes is this molecule called a chlorofluorocarbon. It's the primary anthropogenic human cause of O3 breakdown. You do need to know the term anthropogenic. I've been telling you all that all year, so make sure that you know that term for this unit. CFCs, this molecule here, a chlora because of the chlorine, flora because of the fluorine, carbon because of the carbon. So a CFC. It was used as a refrigerant chemical. So freezers, refrigerators, anything, air conditioners, they would put chlorofluorocarbon in. It's a propellant, liquid propellant that holds cold air. And so they also used it in aerosol containers, hairspray, window cleaners, different cleaners or spray cans, spray paint cans. If you look at some cans now, it'll actually say no CFCs. Manufacturers have moved away from using chlorofluorocarbons. But basically what happens is the UV radiation causes the free chlorine atom to separate from a CFC, and actually it can end up knocking off all of those chlorine atoms. And chlorine is highly electronegative, which means that it is going to strip off one of the oxygens from the ozone molecule, converting it into O2, and it also forms then, when it joins with the chlorine, it forms chlorine monoxide. And so then what happens is this free oxygens that are floating also around in the atmosphere will strip off an O from chlorine. So that just happens over and over. It's a cycle that happens over and over again. And it can either form O3, or that chlorine can go and then, strip off another oxygen. And this just happens over and over. Like I said, one single chlorine atom can actually persist in the atmosphere for 50 to 100 years. So the CFCs that we put in the atmosphere when I was little are still actually in the atmosphere, causing lots of damage. And those can destroy, over those 100 years, they can destroy up to 100,000 ozone molecules. So let's move into let's see if I can go back really quick. We probably should have taken a look at what we're going to be talking about. But we're going to talk now about how we can reduce ozone depletion. And so the main way to reduce this anthropogenic O3 depletion that's occurring with the CFCs that we put in the atmosphere is by phasing out and then replacing all of those chlorofluorocarbons. So global leaders from around the world got together in Montreal, Canada, back in 1987, and they agreed to something called the Montreal Protocol. And this was a global agreement that developing nations, actually nations throughout the world, made to phase out CFCs out of production in refrigerators and aerosols and the other industrial uses that CFCs were used for. They decided to replace those with hydrochlorofluorocarbons. So basically, or essentially, they added a hydrogen to the CFC. The issue with this is that it still depletes the O3, and it still acts as a greenhouse gas. So this is a really nice chart to look at, because here you can see the CFCs have a high ozone depletion potential and a high global warming potential. So CFCs are just bad for both events occurring in our environment. HCFCs, however, have a low ozone depletion potential, so that's good for the ozone layer, but they still have a high global warming potential, and that's not so good. So they're better, but it's kind of like the lesser of the two evils here. So it's not a permanent solution, but it is a stage in the transition away from using CFCs. What we want to end up doing is we want to end up getting to where all industrial purposes are using, or even, for consumers, that we're using these HFOs, which are hydrofluoroxides. And these basically have a zero ozone depletion potential and a very low global warming potential. So it's not a greenhouse gas, and it's not going to harm the ozone layer. That would be ideal. We're doing this slowly in phases, and so the developing nations have said that after 2020, those are going to be completely phased out, and I believe that that's happened. And then developing nations have until 2030 to phase out using CFCs and moving completely to HCFCs. So we are getting there. We're not quite there yet, and we saw how long those chlorines can actually stay in the atmosphere, which is a bad thing. So this is the transition. This is what we want to move to, and that's what's happening. The replacement for our HCFCs, as you can see on this chart, just to make that clear, is something called a hydrofluorocarbon. It's still a greenhouse gas, but it's not O3 depleting, right? It doesn't have that chlorine in there at all. But again, we want to get to the hydrofluorooxides. That would be the ideal. So replacements for HFCs, like I said, are those HFOs. It's basically just an HFC with 2 carbon double bonds that shorten the atmospheric lifetime, and has very low global warming potential. All right, so here is your practice FRQ for 9.1 and 9.2. First of all, you're going to describe how stratospheric ozone protects organisms on Earth from UV radiation, and describe how CFCs deplete stratospheric ozone. And lastly, if I can get rid of my camera, you're going to explain how the Montreal Protocol decreased ozone depletion. Okay, I think that's it for these notes. If you have any questions, make sure you're asking me in class, and I'll see you guys next time.